All right, everybody. Welcome to class. I hope everybody online can also hear through the mic. And if you have any questions, you can ask on chat. I'll be checking that. And then you can also ask out loud, and Shincho will be able to hear you here. All right, so everybody, welcome to the final class of the semester for computer vision. Congratulations on making it through the semester and sticking with the course. We had a lot of fun. Today, we're going to be ending off with a special guest lecture from Shincho. Shincho will introduce herself in a little bit, but just remember to give you context. At the end of the semester, I reserve these last two lectures to go over some of the state-of-the-art things that are happening in computer vision, just to give you a sneak peek of that. And hopefully, as you're listening to this, you'll see how it connects to all the different things that you learned in the class. All right, so Shincho, thanks for coming.
Yeah. Okay, hi everyone. My name is Shincho, and today I will talk about modern approach for multi-object tracking and trajectory prediction. So before I jump into the lecture, let me introduce a bit about myself first. So I'm a first-year PhD student working with Chris, and I was receiving my bachelor from Wuhan University and master here, same as you or most of you, I guess. And I work at Facebook for a while before I joined PhD. So now I'm working on autonomous driving, 3D computer vision, and a lot of similar and related things. And I have my website there, or you can just search my name if you want to see what I'm doing. And that's it. So I think throughout this course, I will introduce some basics and also the state of the art like Chris introduced. But if you have questions, just feel free to interact at any time. And also, maybe if there are questions, Chris, on the Zoom, just ping me because I may not be able to see the things on the Zoom. Okay, so yeah, so first thing, prerequisite for this lecture, and I've checked our syllabus for this course. So basically, I think most of the things that's required in this lecture already been covered in previous lectures, such as perceptron, multilinear perceptrons, CNNs, transformers. But I will not really dive into the details of this because it's kind of beyond the scope of this lecture. Maybe just a little bit knowledge about them should be sufficient. And most of the other content of this lecture is self-contained, so you don't need to worry about it. Okay, so before I jump into the actual content, let me give you a quick demo about autonomous driving, because the multi-object tracking and trajectory prediction that I'm talking soon can be applied to autonomous driving, but I mean, you can apply them to any other domains. But because I'm working on autonomous driving, so I want to introduce this part first. So here you can see, like at this particular frame, this is like the typical, one of the typical scenarios that you will use in autonomous driving field, which is LiDAR point cloud. You see there are a lot of points captured for different objects, right? So as I play this video, oh, sorry. There's no play button. Okay. And I think later on you will see other sensor. I think it's radar. Not showing right now. This is my camera image. Okay, so here you see like the light, traffic light has been detected, right? So that's one of the module in autonomous driving pipeline, and go through. And then here, this is like one of the critical components as well. You see all of the objects, such as cars, they have been detected and also tracked because you can see their identity are consistent across frame, and there's also speed or velocity calculated for each object, right? So that's called typically what we call perception. And say it again. Then here you see like beyond these detected boxes, there are also like trajectory on the ground, right? So I think this is like a bird's eye view, but for the same thing. You see all of these trajectories in front of each object. Those are what you believe or where you believe they will move, right? So that's like prediction, which I will talk very soon. And the green one, which is your ego vehicle, yourself. So that's what you will control. And the green lines are basically the planned trajectories or where you will go based on all the information you have gathered from the surrounding objects. And there may be different surrounding objects like pedestrians, cars, and also cyclists. So you want to detect all of them. Right? So, But actually, this is like illustrated demo. This is not a real demo. This is like hand drawn, I think. And this one, I think, is a real demo. This is from NVIDIA, something they released like 2 years or 3 years ago, I forget. But basically, it's doing the same thing. But this is like the real thing. And on the left, you can see the LiDAR printout. And top left corner, that's like the RGB. And this is the detected objects and also predict trajectory, as you see those lines, overlaid on the graph, the same graph, or the HD maps you have, because you want to know where the name is, right? And where you can drive, where you cannot, right? So that's the HD map people normally use also in task driving as well. And basically that's what people normally do in industry or in academia and where we are right now. And we can do pretty good predictions, but still there are some corner cases we cannot really solve at this moment. So that's one of the challenges which I will talk about soon. Yeah. So I think given those two demos, hopefully that's kind of like a overview about what we're doing. And here is like a high level diagram to illustrate all the components inside this pipeline. But we will not talk about all of them. This is just give you a high level introduction. So on the left, that's the sensor, the LiDAR point cloud, the radar, and GPS, IMU, and also images, something that you're most familiar with. And in the middle, there are 4 important modules, right? Localization and mapping that give you the information about where you are, the ego vehicle. And perception give you the information about where the surrounding objects are. Prediction, which is like the predicted trajectories to inform you where others will move, so you can make according plan based on that information. So that's done in the planning and control modules, right? And the plan action will be sent to the controller that will basically just drive your car. Sometimes there will be also communications between other autonomous vehicles, so you can do better coordination between multiple AVs. Okay, so like I said, I will not talk about all of them today because that's like that will become a very long lecture, which you don't like. So I will just talk about perception and prediction, and let's just quickly look at the specific agenda that we'll cover. So first, I will talk about the foundation, which is like the idealized multi-agent trajectory prediction. That's like a simplified case, which will not be able to be directly applied in the real world. That's like the foundation, which we have to learn first. And then we will talk about 3D modular tracking. The reason is that if we want to do prediction, we want to understand where the object will behave or will move in the next few seconds. We have to first understand where they are right now and in the past, right? So that's like the information gathering from the past, so they can do whatever prediction in the future. And then there will be some advanced topic that will cover use the interface between these 2 modules, tracking and prediction, because if you consider these 2 modules individually, there will be some issues that you cannot really, for example, you cannot do robust prediction because there are some errors in the tracking. So how do you deal with them? How do you improve the prediction based on whatever information you have in the tracking class? Okay, so yeah, I think that's like the basic introduction. Any questions so far? So that's really like a high-level overview. Probably not. But if there is, it can be about like autonomous driving in general, because I will not talk about them in the next, but only the 2 of the modules, the tracking and prediction. Okay, so let's delve into the first part, multi-agent trajectory prediction. So the goal is very simple. Like I draw 3 trajectories here. The red, green, and blue. So they typically represented in a very simple form. Basically what I wrote in there. Like each trajectory, you can think of just like X, Y, or UV coordinates on the ground, right? So that's like just 2-dimensional data. But because you have multiple agents, and each agent has data in multiple frames. This is for the past frame. Here we developed as m total frames, and we have k total number of agents. So the total input data is then represented as a matrix with dimension m times k times 2. That's clear? And then we're going to feed this input to the prediction algorithm. So that will give us some output. And we want this output to be as accurate as the ground truth, which is like their future trajectories of the agents we have observed, right? So here we have 3. That means we also predict 3 agents. And each of them has like a very similar form as the inputs, right? So here I use y to denote the ground truth or the output. And the only thing changes here is that we have n frames rather than m, because, for example, if you want just use 1 second of past to predict, let's say, 3 seconds of future, right? So the n is bigger than m, but the key is the same. So that's basically the input and output we have for this task. And goal is to basically understand the motion pattern of all of the objects we want to predict, right? Because if you want to know where they will move, you basically just need to understand where, like, how they behave in the past. And also we want to understand the joint interaction between multiple objects, right? This is like pretty straightforward because other objects might affect the behavior of yours, right? Because, for example, if there are objects in front of you, you don't want to collide with it, so you might take a different path to avoid collision. So that's kind of like the interaction or the effect coming from the nearby other objects. So that's basically what we talk here, or what we call joint interaction model. Okay, so that's basically the goal. Is that clear? Yeah.
You said n should be greater than m, right?
No, it's not necessarily true. I mean, n could be anything. So, but typically, I think you can predict whatever frames you want. For example, you just predict 1 next frame, or you want to predict 10 next frame, or 100 next frame. But it's just a matter of how accurate it is, right? Because sometimes the longer you predict, it's less accurate, right? So the n is basically some number you choose based on your need. If you want to understand the longer term behavior of the object, you just predict longer, right? Yeah, so it's not necessarily to be larger than m, but you can choose.
But can n be greater than m because the data we have is less and we are trying to predict bigger trajectories?
I mean, yes. So that's why I said like typically n is bigger than m, right? Because you want to predict longer. And in fact, I think right now,
I think there might be some confusion. I think
yeah.
K is the time index.
No, K is the number of agents here.
K is the number of agents.
Yeah, M and N are the number of frames.
N is the number of frames.
Yeah.
You're saying the future window of prediction can be variable.
Yes.
It can even be longer
or shorter
than the observation that you have, or it can be shorter.
Yes.
Okay.
Yeah. Is that clear? Yeah, and in general, I think people are now moving towards longer term prediction. For example, N can be 8. I mean, that depends on the SPS, but typically we want to do like 8 seconds of future prediction, because the longer you predict, you can get more information, right? You can do more safe planning, right? Because if you just predict 1 next frame, it's maybe not informative. Yeah. Okay, so that's like the input output, really basic thing. And now let's look at approach. Oh, oops. So yeah, the first thing is like, let's forget about state of the art right now. Now let's first build the simplest approach that we can think of, right? There are actually many ways, but is there any people think of like the simplest thing you can do here? Like based on input output we have, like what we can do about it, like what we can fill in the blue box, the prediction algorithm. Think about what you have learned.
Linear interpolation.
Sorry?
Linear interpolation.
Yeah, or actually linear extrapolation. Yeah, so because you want to predict the future, right? You are not interpolating between the past, right? So that's typically called linear extrapolation. And actually, I just kind of clicked it. Also, you can use Kalman filter. I think some of you may learn from the other course. But basically, what you do is that, like the simplest or the stupid thing you can do is like just use the last 2 frames of data you have, you subtract between them, you calculate the velocity, right? And you just add that velocity into your current location to predict the one next frame location. And then you can keep doing that. And then you can get all the future locations. That's pretty simple. And what about something else? Any guess? Like, this is like non-learning based, right? You don't need to use any deep learning, but what about learning based approach? Any guess? Sorry?
Any form of recurrent neural.
Yeah, but what kind of neural network? Convolutional or recurrent? Yeah, okay, but I don't think we cover recurrent neural networks in this part, right? But you're right, yeah, we can do recurrent neural networks. Anything else? But actually, that's a little bit advanced. I'm thinking about more like basic thing we can do. No guess? Maybe like give you some hints. Did you learn this one? Multimodal perception in this course? Okay. So that's probably the simplest or the first thing you learn, right? In this any kind of deep learning based course, right? The first or the simplest neural network that's composed of multiple layers of perceptions. Okay, so how can we exactly do it if they say we use multimodal perception, right? So again, I put the input here. So, okay, so think about it. If we want to use multimodal perception, what the input should be, right? Like, if you have a 3-layer multimodal perception, how do you, like, what's the input format? Like, can you fit an image into a multimodal perception? No? Why? Because the format is not compatible with multimodal perception, right? But, so what do you use typically? Vector? Yeah. But here we have like data has the dimension of m times k times 2, right? So that means we need to do flattening, right? So that gives you like a vectorized feature or vectorized data. Here is not even feature. And then you can fit into multimodal perception, right? That's pretty simple. And just output whatever dimension you want. But here it's like 2 times k, 2nk, right? And that means the multimodal perception has the dimension of 2mk to 2nk, right? Any problem? Is this something that you think is feasible to do? Let's say write in your code in a pretty simple way. I see there's some discussion. Any question? Or no? Okay. And then you can train this network just using R2 or any regression loss, right? That's very simple. Okay. So I mean, there could be even crazier way, right? You can even do it with CNN rather than multimodal perception. Because if you look at the data, right, the data is m times k times 2. That's pretty similar to an image, right? What's the dimension of the image? Yeah, it's like exactly. So it's like we just change the number of channels from 2 to 3. From 3 to 2, right? And the H and W is a little bit different here. Okay. But that's actually not like it's not a smart approach because, as I show here, because it destroys the property of permutation invariance, right? What does this mean here? So if you think about this trajectory data, if you permute their order, so basically this vectorized data, right? You can, let's say you can put this green trajectory in the first row of your image, or you can put the red trajectory data in your first row of the image. If you want to construct the image, right? This m times k times 2 or first column, sorry, right? So you can just replace the row index of each trajectory, and the result should remain the same, or just like you just change the order of the results, right? Because the result is it's also trajectory. But for the image processing, if you use CNNs, it actually matters. If you switch the row of the image, you will kind of change the results a lot. So that's why I said CNN destroy the property of permutation invariance. So you can do it, but it's not like the best approach you can take. I think, to my knowledge, there's no people nowadays do this trajectory prediction using CNNs. I mean, you can use CNNs to extract some context feature from the image, but we're not using it to process trajectories. Maybe there's a way, but I don't think we typically use it. Yeah. And okay, so That's for CNN, right? But for multilinear perceptron, for this approach, we just think of any problem with it. Any of you can think of the issue with this approach? It's okay. It's an okay approach, but is there any problem with it? Or you think it's perfect, sufficient? We can just deploy it in our autonomous driving cars, and you can just sit in it and don't need to worry about the safety. Yeah.
The number of agents is very important.
Exactly. But what will that cost? Like what issue?
Instead of the side difficult.
Exactly. Okay, so that's basically what I put here. So how can we, maybe for some students didn't hear that community, basically the K can change, right, across frame. Let's say right now, we have, let's say, I don't know, 80 students, but maybe in like 10 minutes, two students go to the restroom and we have 78, right? I mean, so the number of K is changing over time, and we don't know the exact K in advance. So that means this MLP, the number of parameters, we don't know exactly in how many we should have. Right? So how can we deal with that? Any smart idea? There are some techniques you have learned in this course to deal with this. So you have a variable size of input, and you still want to have a level to learn feature from it. How can you do it? Too hard? So maybe I can provide a hint here. So like a very light way, you can independently process each object, right? We don't process all of them together. We just predict one at a time. So that means you remove the K. The K becomes just one, right? So the network just needs to process 2m times 1, not 2mk. Then it's fixed, right? Because the m can be pretty fun. Let's say you just want to use past 2 frames. Then m equals 2. Right? So that's simple, right? But this also causes another issue. If you remember, like I said in the beginning, there are two basic goals of trajectory prediction, or two basic aspects we should consider during trajectory prediction. And one of them is understand the joint interaction between multiple agents, right? So if you process each agent independently, you don't really know where other objects are. So that means you may predict some weird trajectory where like trajectories that are not feasible to happen. For example, if there's another trajectory in front of you, you predict that I will just penetrate that object, right? That's possible, and you don't want to do that. So now comes to this part, like social interaction modeling for trajectory prediction, right? Because you want to understand how you can model that better, and it's better than independently process each object. Okay, so far any other question? I think this might jump to another part. Yeah.
Instead of we introduce, can we like have a matrix to any maximum number of objects we can process, so the size of the network could be fixed?
Yeah, I think you can do that. So you're saying you can do zero padding, right? I think you can do that, but I mean, there are probably two basic issues as well. One is like you probably don't have a good number of the maximum number of objects, right? Because sometimes if you go to crowded city, probably you can go like hundreds. But for the residential place, maybe just a dozen of objects. So I mean, it's definitely feasible, but you probably don't know how to properly do it. And another thing is you're wasting a lot of resources.
Yeah, that's true.
Right? And maybe zero padding will cause some issue for the existing object as well, because you're adding some noisy data. I don't know, maybe network can learn it, right? Because you just add zero, so they might just learn to ignore it. So that's a feasible approach, I would say. Yeah. Okay, so that's for that's another approach to do social interaction modeling for trajectory prediction. But what are other like smarter approach? That's something we will talk about right now. Okay, so again, this is just based on what we just discussed, like independent process each trajectory. right? So what we do is pretty simple. We just flatten each trajectory independently, pass through a multi-net perceptron. So that's what we just talked, and we obtain an object feature for each of them. And the dimension of the multi-net perceptron is it's determined. It's pretty clear. It's 2m to c, and then we have this like output multi-net perceptron, and you can merge them into a single one either way. And then the output trajectory for each one, and you just put the result together. That gets your that finish your I think the entire processing. But like I said before, how to model joint interaction between objects and in a smart way. So one thing people have tried. This is something that I said before. You probably have learned, right? Do you learn this before? Pooling in the CNN lecture, right? So when you do image processing, sometimes you also have like variable size of image, and you can do pooling. But pooling can be also used for other purpose, like increase the receptive field, right? Or you just want to downsample, for example. But I mean, here we can do pooling as well, but just for the purpose of summarizing the feature from all objects, but in the same time, it outputs a fixed size feature, right? Because it doesn't matter what the k is, you just summarize into a single vector, right? So that's basically what we show here, the green one. That's a feature, includes, like after max pooling, for example, you can use max pooling or average pooling, whatever you want. That summarizes features from all objects. And you have multiple copies, right? Because you want to pass that information to all of the objects. And you concatenate it with the features for each object you already have. That's pretty simple. You just have a longer vector. And then that's like 2sig, right? The length of the vector after calculation is 2sig, so that's why the MLP dimension is changed a little bit in the output. Okay, and this is something I said, the put feature summarizes features of all objects. So in this way, you can do joint processing of all trajectory, and you don't need to worry about the variable size of objects. Okay. Then we can call this like object independent prediction because you're doing them separately in the encoder and decoder, but you're doing like social pooling to do kind of interaction modeling. So that's a okay approach, I think. And typically people call this first part encoder and last part decoder. And then you can replace them to something else. That's what we are going to cover right now. Yeah, and then this is like abstraction of what we just draw in the last slide, right? We have the encoder, we have decoder, we have some sort of interaction model in the middle. And this is like social aware feature because it includes feature of other objects, not just yourself. Yeah, so this is like next important question. What else can we use beyond the multi-net perceptron plus pooling? What else can you think of? I think the student there already said we can use recurrent neural networks, right? So that's one of the things. Another thing, sorry? Attention? Yeah. Anything else? Attention is good, yeah. I think I already put transformer here. Yeah, but I think, yeah, there actually can be other approaches as well beyond recurrent neural networks and transformer. But basically, what you want to do is to process this vectorized feature, or like this trajectory data, right? So probably, like except for CNN, maybe like you can think of other approaches as well beyond these two. But even within these two, we probably just mainly cover the first one because the transformer, I think it's already covered in previous lectures, right? Yeah. So you might want to think about offline how to do this with transformer. But let's jump into the first one because I don't think this is covered in previous lectures.
There was a question online that says, can you please explain the pooling module again?
Yeah.
Output shape seems to be the same as the input.
Yeah.
What pooling is being done here?
So like I said, you can use average pooling or max pooling. So that's like the name of the pooling module. But what exactly it's doing here is like the input, you have three features here, right? Let's say the three features each have a length of 10 or anything. And then for each index, for each index of that vector, since you have 10, you just find the maximum value across 3 features: the green one, the red one, the blue one. Find the max one among the 3. You just use that maximum value, put it into the green feature, the put feature. That's what we call max pooling, right? You find the maximum value for each index of the vector, and then you get one feature, one put feature at the end. But why I'm showing here have 3, because I just copied the same feature 3 times. So that means the put feature has the same dimension as the input feature. It's just like no matter how many input feature you have, you just have a one output feature at the end.
And the students say, got it, thanks.
Okay. Okay. Thank you. Yeah. Okay. Recurrent neural networks. Yeah, I think we have covered 30 minutes. Maybe I'll quickly go through this. So we already talked about how to do like multi-neural perception, CNC imperial connectors. That's basically some structure like that, one-to-one mapping, right? Because you have a single input and you have a neural network that gives you a single output. The input output has a one-to-one mapping. But sometimes we don't want to do this one-to-one mapping. We want to do like one-to-many or many-to-one to deal with different cases, especially for trajectory data or for sequential data, right? So here we have other 4 variants. So first question to ask is, which one do you want to use for the prediction encoder? Because we want to adapt this kind of model to do trajectory prediction, right? Which one do you want to use? Many-to-one? Yeah, that's correct. For the encoder, we can use many-to-one. Yeah, actually you can use many-to-many as well, but I mean you will throw away the previous 2 because you don't need it. But that's like only for the simplest approach. For more advanced approach, actually you can use all of the features in the many-to-many diagram, but basically you just, let's say, do some attention all 3 to further summarize into one feature. But for the simplest approach, you're correct, we can do this many-to-one, right? But for the decoder, which one do you want to use? Sorry? One-to-many? Yeah. That is the most simplest approach. Yes, we can do one-to-many. But again, we can do many-to-many as well. So both of them are many. The reason that we can do many-to-many is that, especially this many-to-many, just for the decoder, because we want to use predicted results, the first blue, and backpropagate as the second red here as input. So that's something we call autoregressive prediction, right? You use the prediction in the last time step as input to make the next frame's prediction, and you do that iteratively. So that's autoregressive prediction, and combining those 2, we can do this fourth one, this many-to-many, for like combining encoder and decoder, right? So you have 3 red data, that's like past trajectory. You want to predict 3 blue future locations for each agent, or you can do joint prediction as well. Okay, so here's a closer look, but actually it's a pretty simple, right? So inside this is like an example for many-to-one case. Inside each green module, you have like the input from the red. That's like your input data, the X past trajectory at one particular frame. And then you also have the green arrows coming from the net, right? So that's something you can think of like a memory, right? The network has memorized something from the last time step, some kind of information you want to pass through to the next time step. We typically call it like hidden state in recurrent neural networks, but I mean you can call it any way you want. And that's edge basically, the memory information. And X is the input, and you just feed them into some function that give you the new state for the new memory information that pass through to the next time step. It's pretty simple, right? And what do you think we can use for the F here, the function? Again, it's like pretty simple question.
MLP.
Yeah, you can just use MLP, right? Because again, these X and H, they can be both vectorized features or just vectorized data. And we want to use the phylo hidden state, the phylo H, which actually not goes to the right, but goes to the top. The blue one, that's like the phylo feature we want to use to summarize all the information up to now. Yeah. And probably I will skip this because it's containing too many information. But for some of you have already learned the machine learning course, right? The LSTM is just a special form of RNN. And instead of using one MLP, you just use multiple MLPs inside each module, right? Just have more W and B, right? The W means the weights of the Phoenix linear, B is the bias. It just has like different kind of state for get inputs and output bits, and you have two kind of memory, not just one, which is the hidden state. You can also have a cell state to make the information propagation more direct, so that you can deal with one issue in the standard recurrent networks. That's like you probably cannot memorize the information very well from the past. So that's like one issue in the vanilla recurrent networks. Like after a few frames, the information from the very first frame kind of being completely forgotten. You don't want to do that. So that's why people propose this and also propose something else after LSTM. And the reason I'm talking about this LSTM is that it is used in one of the CLR approach a few years ago, which is called Social-LSTM. So if you remember the general framework that I introduced before, where you have encoder, decoder, you have social modeling in the middle. What they do is like exactly like that, right? They just replace the MLP in the encoder and also decoder with LSTM. Pretty simple, right? There's nothing else, nothing magic. This is a CHR paper. You can also publish it if you are born a few years earlier. Right? There's nothing fancy, right? And also they do autoregressive prediction. Basically just many-to-many in the decoder, right? Rather than one-to-many. That's also kind of basic thing. And for the output, here we draw the output as XY or UV coordinates, but you can extend that 2 dimension of the output to 5 dimensions or 5 channel. Basically, you can use a bivariant Gaussian to represent basically like mean and variance for each dimension, like U and V. That's like 4D data, right? And then also you want to have the covariance for this bivariant Gaussian. So that's like 5-dimensional data rather than 2 dimension, like just UV. Because in this way you can get some uncertainty, like what's the probability, like where the object might be, rather than just give me the final XY coordinates. And here is a visualization copied from this paper. Basically, you can see here there's 6 pictures. They're just representing the predictions as 6 time steps. T equals 1, 2, 3, 4, 5, 6. 6 future frames. And each of them, there are 2 figures. The top one is the actual XY they find. Basically, just the mean of the bivariant Gaussian they estimate, right? And the bottom one that has some heat map. This is basically including the this is like visualization of the Gaussian, right? So you have the mean and also variance. And basically, you just predict the objects to move one like a little bit at one step and then move a little bit more, and that's it. Okay, any questions so far for this Social-LSTM or any like social interaction modeling questions? No, but I think you probably agree this is like a very simple approach, right? We just come up with the general framework, but just what they do is just replace the multimodal perception with LSTM, right? Okay. And then let's just talk about a little bit more advanced, maybe just the first one. I think maybe we'll skip the second one. The first one is pretty important. It's called multimodal prediction. This highly correlates with one of the previous lecture. You already checked before, which is about the GAN and VAE, right? So the basic idea is that we want to do stochastic prediction rather than deterministic prediction. So that's what we call multimodal here. And the reasons are pretty straightforward, right? People's intent, including yourself. I mean, actually, in multi-agent trajectory prediction, we don't really know, or we don't really have the location of the self agents. We just predict trajectory for all agents. But sometimes you want to differentiate the ego agents with other agents. But in any case, people's intents are uncertain, right? Because you don't know where their destinations are. You don't know where they want to go ultimately. So that's one thing. And also, even you know their destination, you don't know, like locally, how they're going to be paid, right? You can take a different path. I can go straight to the door. I can take a right turn a little bit, or take a left turn a little bit, right? So that's like a local planning or global planning. So both of them, you are not certain about it, right? And also the environmental factors are not modeled, right? You don't know the map. You don't know the scene, right? Here there's a chair, so I can't just go straight. So I have to take into account of that. So that's kind of information you need to tackle. You need to consider when you do prediction. Like in autonomous driving, like I showed in the very beginning of the lecture, there's a map people typically construct for where the lane is, where the bridge, where the curves are on the road, right? So that's like environmental factors. If you don't model that, that kind of also inject more that stochasticity or uncertainty into the question. So that's why you want to make multiple predictions, because if you just make one prediction, maybe it's wrong, or it's high probability. High probability that it's wrong. So we need to generate multiple samples of prediction, and we might need to consider all of them to make the planning safer. But actually, I think right now in the planning literature, there's still no way to go. Like typically, even if we predict let's say 5 or 10 samples of prediction, but not all of them are really used in planning. The similar approach in planning, you just use the most probable prediction produced by your prediction algorithm. You don't consider the rest of prediction, but that's not so good. We really need to consider different kind of possibilities of the people's or other vehicles' behavior. Okay. And here I just copied like two basic framework people use to do stochastic modeling, right? The GAN V, something you have there. Right? Again, you have a discriminator and generator. And in the V, you have like encoder, decoder. And then in the middle, you estimate the mean and variance of the posterior and or the prior distribution. So you can sample from it, from the latent space, to get multiple results or multiple samples. So that's something you already learned, right? Is everyone familiar with this or no?
We only covered GAN. We didn't cover VAEs.
I see.
They did autoencoders for the
I see. Yeah, actually, I think that aligns with this PPT as well, because I didn't really include a method to incorporate VAE to the prediction, but I do have some slides later to talk about how to incorporate GANs for trajectory prediction. But in general, both of these two approaches can be applied to do stochastic trajectory prediction, right? Okay, so how do we adapt them to do trajectory prediction? So here, first let's consider GAN. I just copied two pictures here and zoom in just for a close comparison. So what do you think, like where the modules in GAN and in the general framework for prediction are similar? Like what modules are similar in these two frameworks? Anyone has a guess?
Prediction labels.
Sorry?
Prediction labels.
Prediction labels. You mean this one, this green box?
Yes.
Yeah, and then what it corresponds to?
Corresponds to the predictions of the regional pipeline.
You mean that one?
Yeah.
Actually, no, because here the prediction labels are from the discriminator network, right? You want to predict if the image is fake or real.
Oh, it should be from generator.
Sorry.
I mean, it should be the result of the generator, and
which is here, right? The fake image. Yeah, that's correct. So the prediction corresponds to the fake images. What else? I mean, there are so many correspondences.
Real images are the ground truth.
Real images has and the ground truth, right? Yeah, that's correct. The real images and the ground truth, they are the same thing, basically. Sorry? The discriminator, is that?
Instead of L2 loss, that can also be a discriminator like thing, telling if the prediction corresponds to a real path
Yeah.
of the object.
Yeah, exactly. So that's what we are going to do. That's what's missing here, right? Because actually we don't have a discriminator in this prediction framework, right? Do we? We don't have a discriminator here, right? So you're right. So that's something we're missing here, right? So first of all, I think someone already said this real data corresponds to real images, right? And also, actually, the fake image corresponds to prediction. So also we mentioned the other thing is the generator network, right? We already have it. The entire thing is the generator network, right? We use it to generate predicted trajectories. And what's our missing? We don't have the discriminator network. We don't have the noise vector, right? Because we're going to need the noise vector to generate different prediction samples, right? By varying the noise. Okay, so after that's clear, it's very straightforward to do it, right? First, we just add a discriminator, and then we have the ground truth. That's the real data. We just need to predict if it's real trajectory or like some weird trajectory predicted by a network, right? So that's the first thing. And again, what can we use for the discriminator? Pretty simple question. We know the structure of the generator, right? We want to use LSTM, social pooling, but what about discriminator? Sorry? Yeah. Yes. MLPs. That's correct. You can use MLPs. Basically, this is what we introduced at the beginning, right? We can use the MLP to process trajectories. Or, I mean, you can use ML to process each trajectory independently, right? That's something we cover as well. So basically, you just predict each individual trajectory, if it's a real or fake, right? That's definitely feasible. And actually, you can also use LSTM, right? That's something we just taught. Okay. And also, you can do object-independent processing or just do like joint processing with social pooling, right? That's also feasible in the discriminator. Okay, so next thing, we want to add a noise vector, right? So this is essential. We want to use this to do stochastic prediction. And that's very simple. We just add something more into the features we have. We already have the social aware feature that includes the features for each object about their past behavior. And also we have the feature, the gray one, meaning it's like the social feature, summarizing information from all objects. Now we just add another one, a random noise vector, so that we can generate different noise to get different predictions. But how to construct the noise vector? For example, do you want to make all of the three? Here we have three objects, right? Do you want to make the three noise vectors the same or different? Sorry? They should be different. Why?
Each and every trajectory would behave in a different way. So
each trajectory has different one.
It behaves in a different way, like each trajectory, so it makes sense to give different noise vectors for each one of these trajectories.
Yeah. That's definitely reasonable. So actually, that's I think one feasible thing to do. We just have different noise vector for each object, and actually, I would think even if we use the same, that's not stupid. That's also feasible, right? It just means that there has some correlation between them. We can use, because you use the same feature for each one. It's like the social feature, right? You just have 3 copies of the gray feature for each one. That's definitely feasible. Maybe you will reduce the diversity in the prediction, right? Because everyone is the same thing. But I think these two are written here, the same noise vector for all objects. That's okay. And also you can use random noise vector that's different for each object. That's also okay. I think in the original paper, okay, we haven't really covered the paper. It's in the next slide. But actually there, yeah, sorry.
Is there any reason that the noise vector is added after pooling compared to before?
I think that's a good question. You can add it before, but if the reason that's I think this is my guess because I'm not author of this paper. If you add it before, that will go through the social pooling, right? And that's really because the goal of the social pooling is try to summarize feature from all past behavior of all the objects. But the noise vector, that's not like the past behavior. It's like just some random thing you added on top, right? So it's not reasonable to give it to the social pooling module, right?
That makes sense.
Yeah. But maybe the author has a better answer.
Well, you can put it there. So if they're all the same, then it doesn't matter if you pull, you get the same thing out.
Yeah, yeah.
If they're all different, and it's really random noise, you just get a zero vector out.
Yeah, exactly. But again, that's like not informative thing.
Yeah.
Right? Is there some additional redundant feature there? Yeah. So I think that's why they just put it afterwards. But you can do it beforehand. I don't think it will really make the performance a lot different, right? Or you can maybe just put into the input data even before that, right? But let's go back to the noise vector construction. There is actually another or other ways beyond these two basics. Probably this is something you haven't learned before. So you can enforce these two to the you can do these two at the same time basically. So first you can have one universal noise vector. That's like just one for global, like for all objects. And then you can condition on that noise vector, go through some neural network, and generate 3 different noise vector for each one, right? And then you just inject those 3 for each object, right?
So I just want to know when you want to predict trajectories, what do you consider as a real trajectory? Because even if you're a few steps off, you're still having a plausible trajectory.
You mean the future or in the past?
In the future, if you want to predict. So, what is the kind of loss you're using? Like N2 loss does not seem to make sense. Like even if you're a few steps off, it's still plausible.
Yeah, exactly. So that's why people use something more advanced than L2, because like I said, if it's a little bit off, that's still plausible, right? But you shouldn't really penalize it because it's off, because it's also reasonable trajectory. So there are multiple ways of doing that. I think we will cover one, which is called best of K or best of N regression or best of N loss, because let's say you make 10 predictions and maybe all of them are plausible, but there's only one future trajectory in your ground truth data that actually exists because the data is offline pre-recorded. So you just find the one prediction, all of the 10, that is closest to the ground truth. You just minimize that one, because that one corresponds to the prediction you want actually just match or align with the ground truth. The other line predictions, they might be plausible, but because they are for other modes of future or different futures that don't actually exist in your ground truth data, so you don't penalize them. It's like best of K prediction.
But in this framework, you do penalize, right? Because you have a discriminator with.
You mean the discriminator?
Yeah.
In this case, let's say if you have multiple ground truths, then you don't penalize, right? So if you only have a single ground truth, yes, I think so. But actually, there's one paper published last year or 2 years ago. They generate multi-future ground truth data in a simulator, right? So that's one way you can do, but actually it's a little bit cumbersome to generate that kind of data. Yeah, but I think typically people most likely just use the best of K or best of N whatever predictions to do the evaluation and also do the training optimization. But there are more advanced approaches. Yeah. Okay. So yeah, there's another thing I want to mention, which is here we are doing actually conditional GAN rather than the vanilla GAN. Why? Because the generator, if you look at the GAN figure here, the generator only takes noise vector as input to generate some data or fake images, right? So this is not typical GAN. But here, our generator not only takes a noise vector, but also the features of the optics. So this is called conditional GAN because it conditions on some context. Here, the context is just the feature for the objects that's kind of including the behavior of them in the past. Okay, so that's the context. And in the same way, when you do the VAE, you have the conditional VAE to do trajectory prediction. Yeah. But I don't think we will have time to cover VAE. But here, these are results for the conditional GAN-based trajectory prediction. On the columns, there are 4 samples. Like I said, because you're using GAN, you can vary the noise vector, so you can get multiple predictions. Right. So here they just draw 4 predictions, and each row index each row means like different situations, different data. So if you just look at the first row, the blue ones are ground truths, which is the same across 4 samples because there's just one single ground truth. But for the predictions, the red and blue, the red and green, the varies a little bit, right? For this one, it takes a left turn to move this way, but in this one, it kind of hits this car actually, right? That's not good, but that's what the level predict. And this one, a little bit right turn to pass away this car, and this one is trying to make a U-turn even, right? So the predictions varies across different samples. So that's how the stochastic prediction has been used. And yeah, like what you just said, how do you evaluate multiple samples? Maybe, yeah, actually this is pretty simple. So like I said, we typically just use best of. Here I use S rather than N or K because N or K are already used, right? N is used for the number of frames, K is used for the number of agents. I don't want to overload the term. So best of S predictions, meaning that you only minimize the ones, or you only evaluate the one that's closest to the ground truth out of S samples. And the equations are pretty simple. In the middle, you have this Y hat minus Y, and the L2 normal of it. This is basically just L2 distance between the prediction and the ground truth at a particular time step t for a particular agent k. And there are big k number of agents. Here is like just one agent. And then you summarize over all time step, which is n. And you summarize for all agents, right? So you want to compute the distance for all time step for all agents, but only for the sample S that's minimize the distance, right? So that's called best of S prediction. Is this clear? This is just L2 norm over number of frames over number of agents, and take the mean over the best samples you have. Right, and then there's another thing here. It's called frame mask, FM. Basically, it means that in the ground truth, let's say if you want to predict 10 future frames, but unfortunately in your ground truth data, this object disappears after 5 frames. Let's say you just move out of the camera view or out of the LiDAR view. You can't see it, or it's occluded. You don't have the data of it after 5 frames of future. So you only evaluate for the ground truth data exists, right? Here it is 5, and it just masked out another 5 future frames. There's no ground truth. And then the n, then because you want to divide it by the number of frames, you calculate it, so it's not n anymore, it's n banded, because for this object you only have 5 banded frames rather than 10, right? So this is pretty simple. Again, this is like additional mask, like for practical purpose. And this is called ADE, why it's average displacement error, right? you just do average and you calculate distance or displacement. So that's why we call AD, and FD is like final distance, final displacement error. It means like at the final step that you want to predict, the final frame, how is the predicted location away from the ground location. It's like measure the desolation or like the end goal of each agent, right? So that's why we use this one-time step rather than summarize the n-time step. The one-time step that we calculate is only the last time step where we have the data, which is why it's not, the subscript is not n, it's tk, because like I said, the object may disappear after 5 frames or after some frames, so you might not calculate at the end, the big N frame, the final step that you actually want to calculate, because you don't have data to just calculate up to a point where the ground truth still exists. So this is like the typical evaluation, like everyone does in the, even like right now, 2021. So like I said, also it can be used in training to do the optimization, considering multiple predictions are plausible. And here is like the evaluation for this social GAN approach. Basically what it says is that if you predict more samples, the x-axis, the errors goes down. It means that different samples are different, right? So if you predict more samples, maybe there's one that's closer to the ground truth. So it minimizes it has like smaller errors compared to the ground truth. That's basically it. If you don't use stochastic prediction method, you just have one sample, right? So you don't have this kind of error goes down because of more predicted samples. And also, if your stochastic prediction algorithm is not that diverse, you're predicting just exactly the same or very similar predictions for multiple samples, then your errors won't go down for more or bigger number of samples. Yes. Like I said, I'm not going to talk about this, so I will just leave this offline for you to think about it. How to incorporate VAE to do prediction or stochastic prediction. Okay, so any other question? I probably just skip the second one because we ran out of time. Yeah. Any questions so far for the GAN-based approach or stochastic prediction in general? No? Okay, that's good. Yeah. And you're good as well, because if you really understand that, you're pretty close to the state of the art, like 2021 or maybe 2020. Because even right now, what people do is just like multimodal prediction using GAN-based. We're just making the GAN or VAE a bit more complicated, but it is still like the basic framework we just introduced. And here is like a taxonomy or the full picture of the literature so far. And there are many like leaves, if you see here, and we cover some of them. For example, here you see this like modeling approach and pattern-based or learning-based, right? So you can use non-sequential model, which is MLP. We can use a sequential model such as LSTM or transformer or any kind of thing. But we didn't really cover the physical-based or planning-based. That's like a little bit more advanced work. I mean, maybe not more advanced. It's like just different aspects, different types of approaches. And they are less popular right now. And here, we use target agent cues, such as motion state, which is like this XY or UV coordinate. But sometimes you can add velocity or acceleration, right, as the input and output. You're not just using the coordinates, the location of the objects. Or you can use articulate toes, right? Hit the key points. Not sure if you have there in this course, like the human key points or vehicles. You can also define some key points or thematic attributes, right? The class label for each object. That's like additional information you can use, because, for example, for pedestrian, it may move slower than the vehicles, right? So that's some other information you can think of. And the dynamic environmental codes. So you can consider each object individually, or you can consider them jointly in a group. So that's other aspects. And also, yeah, this is like really widely used queues. For environmental queues, you can consider the obstacle where they are, how they will affect the trajectory that will predict. And also the map aware. This is something really popular right now in 2021 or 2020. You consider how to use high definition maps generated offline to really constrain where your prediction should be, right? Because you don't really want to predict the trajectory of your vehicle off the road, right? That's something not reasonable. And multimodal prediction we cover. This is sync consistent prediction. It means that you want to predict all trajectories jointly, right? For example, you can predict one object move to the left, one object move to the right, and they collect, right? That's something you don't want. You want to make them consistent, right? So you're predicting trajectories that's compatible with everyone. It's like sync consistent prediction. And the heat map or scene level prediction, scene level based representation. This is like just use different representation to do this task. You can use coordinates or you can use heat map. I think this is more like closely aligned with the CNN-based approach, right? You can learn some heat map based data rather than like just the coordinates. Okay. We have 15 more minutes, Chris, right? So maybe I will just cover the checking part, not the final part. Yeah. So like a very critical question, right? So we have talked about how to do trajectory prediction, but where the inputs come from? If we don't have inputs, we can't really predict, right? It's like a very basic question. Basically, something shown on the left. And typically, if you just want to do trajectory prediction in isolation, you just use ground truth, right? This is pretty simple. You have the ground truth data in the past for the past and for the future. You just use the ground truth data in the past to predict the future trajectory and measure how close they are correspond to the ground truth future trajectories. That's good enough. And however, in the real world, if you want to drive a car by autonomous driving, right, you can't really have the ground truth path trajectory because you can't really label on the fly, right? When you drive, label the path trajectory. So what's the best way to get it? I think I already showed it at the beginning, right? That's like something we call perception. Right? So the perception modules give you the information about where the objects are right now and in the past, and then how they are associated to each other across frames. So that gives you some trajectories or estimated trajectory. They are not perfect compared to ground truth, but that's probably the most widely used one to get this input data for trajectory prediction. Okay, so that comes to this second part, the tracking. And again, tracking, you also have to have inputs, right? So that's something what I show here. That's called detection, which we will not cover. But basically, it's I think they already covered in your previous lecture, like the fast RC and the SSD, those kind of thing. You just give some bounding box, but you don't know the identity of the box across time. Most likely, you just detect objects at every frame, right? So that's like frame independent detection. But sometimes you can do video object detection. That gives you some association, and that's exactly what we want. The trajectories, right? So here I'm showing another demo. This is for 3D object detection, right? Because sometimes the 2D box is not enough because they don't have the depth information. That's why we want to have this 3D object detection. It provides you some kind of 3D box, give you the depth, give you the size of the objects in the real world rather than like after perspective projection. Okay, so yeah, so this field is really popular. There are so many papers. If you want to do some research in this field, it's a little bit challenging compared to trajectory prediction. I mean, trajectory prediction has also become very popular. I think this year and last year, but detection has been popular for many years. So this is like more, I don't know, like harder area. So it's more challenging to publish. But that's good. That means we also have mature techniques in this field. Yeah. Okay, so that's for the input, right? And then how can we do this multi-object tracking after we have the inputs, which is still in the top? We have the box individual detected at every frame, and we want to associate them across time to get this colorized box, right? The reason that I colorize here is to denote the identity of each object. And goal is really just to understand the similarity between objects across frame, right? If the two objects, they are really similar in terms of location, in terms of appearance, in terms of everything, they most likely just the same objects, but appeared at two different frames, right? So you want to assign the same identity for them. So that's the goal of this task. And here is an illustrated example. Here we show 3 frames, t equals 0, 1, 2, and you just want to draw some matching between them or connection between them. Right, so you can have this kind of association, or you can have this. You just want to determine which one is better to assign the identity. Like I said, this field is much less explored compared to detection and prediction. If you include the 2D MOT, 2D multimodal tracking, there are more papers, but honestly, in 3D MOT, there are really like few works, even right now, compared to other fields. So I'm working in this field, so it's relatively easier to publish compared to the detection and prediction, I think, even right now. Okay, so I think I will just talk about this approach. It's a very simple one. It's called a baseline for 3D multi-object tracking. This is something I and Chris, we have worked, I think 2 years ago. It has been used widely right now in the community, like has more than 1,000 stars and used in various places, like different companies, they hold challenges or benchmarks. They have used this as baseline or evaluation criteria and something. But actually it's a very simple approach, and it just adopt like a very standard pipeline. That's something called tracking by detection. This is very straightforward because we are using detection to do tracking, right? So that's I think one of the reasons called tracking by detection. But another thing is it's doing some online-based association. So like I showed in the previous figure, where we can have 3 frames of detection, we can associate them. That's one way. Actually, you can have let's say 100 frames of detections, and you just want to associate all of them in one shot. That's sometimes we call batch-based tracking. You track everything for a very long window, or like a very large number of frames in one shot. But another approach is like incremental association, right? So here we just want to associate between 2 frames. So after let's say up to some frame t equals to 100, we have some trajectories, and now we're just going to associate with them with the detection t equals 1, 0, and 1 frame. So that's like a much simpler task, right? Because you just want to do association between 2 frames. Okay, so you are incrementally building trajectory at every frame. And the approach is very simple. First, you have this detection module. This is something done offline or off the shelf, so you don't need to worry about it. You just take a state-of-the-art detector, get the results, right? And that's going to be your input. Next, like I said, it's a tracking by detection approach. So you have associated trajectories up to some frame. And what you're going to do is that you want to do state prediction. You want to predict the location of them in the last frame to the current frame, because that's something you will use to match with the detection. Yeah, so here the question is, why do we assume we already have t, the trajectory at t minus 1? Because we're doing tracking by detection, right? This kind of incremental approach. And this trajectory denoted by t are different from d because they are trajectory rather than detections. So they have identities already. And here there's a magic thing happening. This is called a Hungarian algorithm, or any kind of matching algorithm that can do the job. Basically, what it's trying to do is that you have a set of trajectory, you have a set of detection, so you want to match between them. You want to find exactly one-to-one matching. So that's basically what we call a matching algorithm. And here we use Hungarian algorithm that's like optimal matching between two friends. So it's a local matching algorithm rather than global, where you have more friends, right? So this one actually is very simple algorithm. This Hungarian algorithm. So given the T and D, because they're just bounding box, right? Like I showed before. Bounding box, you can calculate their intersection over union. That's something you learn in the object detection class, right? And that gives you some affinity matrix, like how similar each trajectory corresponds to each detection, based on IOU. The closer they overlap, more likely they belong to the same objects. And once you have that affinity matrix, you just solve it with the matching algorithm, which we call Hungarian. And probably I think I will skip this part. But actually, what it does is like just given this matrix, you just want to find, so maybe use this one. Given this matrix, you just want to find the corresponding row and the columns that give you the maximum similarity or minimum cost, right? So that's like the matching algorithm. And although there are multiple steps here, but actually in code, just one line. You just feed the input, the affinity matrix, give to the algorithm, that give you the the row and column index that you want as the output. So that's in the Python packages, pretty simple to use. And here, once you have this matches, that's D match or T match, right? So you just want to give it back to the database, the trajectory database you have, because the trajectory database you had before is only for trajectory up to the next frame. Now you want to update with the current frame of data. And then you have some unmatched detection and unmatched tracking, right? So the unmatched detection means that there might be some new object coming in. So you want to assign some new trajectory for them. And unmatched trajectories mean that those trajectories don't have detection right now. Maybe they have disappeared. This trajectory disappear, like just goes away from the field of view, right? So that's how you do it. That's something we call birth and death, right? Some objects has born here and some objects are dead. Yeah. And then you can get these kind of results just based on the baseline we talked about. It's pretty simple. You just have the detection, have the trajectory up to the next frame. You do the matching. You update the trajectory database. That's it. And this is for vehicles, and this is for like pedestrians, cyclists, and etc. Because basically you just apply this kind of same technique for different categories of objects. It doesn't really matter what categories of the objects are. Okay, I think that's it, Chris. So the last part is a little bit more advanced. Like you have detection, you have the tracking, you have the prediction. But what about the tracking? Results are not accurate, right? There might be some wrong matching, mismatching. You just didn't really successfully match the objects to the trajectory. Then your input trajectory is not good. The prediction algorithm might behave weirdly, right? So that's the problem you need to solve. And I'm going to jump to the next slide. So that's really something we are facing right now in the field. It's like this full integration between multiple modules, right? You have detection, you have tracking, you have prediction, you have planning. How do you deal with the interface between them? Yeah. And the final slide is basically my thesis proposal, which is happening tomorrow. That's exactly talk about the interface, how we're going to resolve it. So I think that's the end of my lecture today.
All right, thank you very much. So we're a little bit tight on time, but I just wanted to, get some final words and say, thank you for hanging in with the class. I know every semester is very intense at CMU, so congratulations for getting through it. I know you have a little bit more work left. But just remember, you all learned a lot of stuff in this class. We've covered tons of material, right? We started with just what is a pixel, right? And then all the way up to, bag of words, CNN, detections, we did transformers, and then we spent all this time on geometry, understanding camera geometry, a lot of SVD and nonlinear optimization, right? And we've covered so much stuff. So I hope you're really proud of yourselves, making it through this course. So thank you all very much. Great job.
Okay.
Yep, that's it.
Okay.